Engineers traditionally relied almost entirely on physical prototypes, designing a part, building it, and then testing it until it breaks. This cycle is incredibly expensive, slow, and limits a team to a handful of design iterations. Because physical testing occurs at the end of the manufacturing phase, critical failures are often discovered too late. When a part fails in the rig, it forces the entire team back to the beginning. ANSYS provides the industry-standard software engine built to solve this bottleneck through virtual simulation and testing. Instead of waiting months for a factory to produce a test part, engineers use these tools to predict exactly how a design will behave under stress. They can identify failure points and optimize performance digitally before manufacturing ever begins. Modern engineering efficiency relies on shifting the entire trial and error process from the physical lab into a mathematically rigorous virtual environment. ANSYS allows engineers to predict real-world behavior by taking a static 3D model and placing it into a dynamic environment governed by structural, fluid, and electromagnetic physics. While the physics of a crashing car differ significantly from the heat dissipation in a microchip, the underlying methodology used to simulate them remains the same. Every simulation follows a universal 7-step workflow: importing the CAD model, defining materials, applying boundary conditions, generating the mesh, running the simulation, analyzing results, and optimizing the design. This pipeline frames simulation as a rigorous progression rather than a black box of arbitrary predictions. Mastering this 7-step pipeline is key to understanding how engineers translate abstract geometry into predictive physics. We begin with Step 1, importing the CAD geometry. We will track a single automotive brake rotor through this entire process to see how a digital model becomes a functional test. In Step 2, we define the material properties. The software requires precise data on the object's makeup, including density, stiffness, and thermal conductivity. Without accurate data, the mathematical foundation produces unrealistic results. Step 3 involves applying boundary conditions, establishing the real-world environment. We set fixed constraints at the hub where the rotor is bolted down and apply vector arrows to represent the physical braking force. Fixed constraints tell the solver which parts cannot move, while applied loads represent the forces acting upon it. These conditions establish the absolute physical parameters the solvers must obey. These first 3 steps successfully translate our physical assumptions into raw data, readying the model for mathematical computation. Step 4 is generating the mesh. Computers cannot easily solve complex physics equations across a single, continuous organic shape. To solve this, we use discretization, the process of breaking the continuous model into thousands of smaller, calculable geometric elements. Within this mesh, the software solves the physics equations at specific points, called nodes, where these geometric elements intersect. This leads to mesh refinement. Areas with complex curves or regions expected to experience the highest stress require a much denser, tighter mesh than flat surfaces that remain inactive. This creates a trade-off. A finer mesh provides higher accuracy, but it requires significantly more computational power and time to solve. Ultimately, the mesh is the mathematical bridge that turns a 3D drawing into a solvable engineering environment. In Step 5, we finally run the simulation. The software applies the boundary conditions across that mesh network using specific mathematical solvers. The first primary solver is Finite Element Analysis, or FEA, which is the core of ANSYS Mechanical. Engineers use FEA to evaluate structural integrity by mapping exactly how much stress, strain, and material deformation the part experiences under load. This color gradient allows the engineer to visually interpret millions of individual node calculations as a clear map of the component's structural health. This data flows directly into Step 6, analyzing results, and Step 7, optimizing the design. By identifying the red high-stress zones, an engineer can pinpoint exactly where a rotor is likely to fail during a high-speed stop. FEA empowers engineers to reinforce weak points or remove excess material to save weight, with the confidence that the part will perform as predicted. Structural analysis tells us if a part will break, but it doesn't account for how it interacts with the surrounding environment. For that, we look to the second solver pillar, Computational Fluid Dynamics, or CFD. Used in ANSYS Fluent, CFD analyzes fluid behavior, tracking airflow, aerodynamics, and how fluids transfer heat away from a surface. The software calculates the pressure gradients and velocity of the fluid as it moves through the solid boundaries of the mesh. We then layer in thermal analysis to evaluate how the rotor responds to the intense heat generated by friction over time. Even electromagnetic simulations for antennas or circuits follow this same 7-step process of discretization and solving. Whether measuring structural strain, fluid velocity, or thermal radiation, the software fundamentally calculates physics across a mesh. Because these different solvers all share the same underlying mesh architecture, engineers can combine them into singular, complex models. Integrating these various domains leads us to multi-physics simulation. Real-world forces do not exist in isolation. In an electric vehicle battery pack, engineers must simultaneously analyze structural chassis stress, coolant fluid flow, and thermal heat maps to ensure safety. In this environment, one domain impacts the other. For instance, extreme heat can weaken the material properties and compromise the structural integrity of the battery casing. This integration enables the creation of digital twins, virtual replicas of physical systems that remain active after launch. By feeding live sensor data from the physical asset back into the ANSYS model, engineers monitor internal stresses and predict maintenance needs. Digital twins shift simulation from a design phase utility into a tool for continuous, real-time monitoring and predictive maintenance. The primary challenge of these advanced models is that multi-physics simulations and dense meshes require massive amounts of computational power. Cloud-based simulation allows engineers to bypass the limits of local hardware, using scalable remote servers to process complex calculations in a fraction of the time. This increased computing power supports generative design, where AI algorithms can rapidly explore thousands of different design possibilities in a matter of minutes. These algorithms iterate through a vast design space, carving out shapes based entirely on the simulation parameters and boundary conditions set by the engineer. ANSYS provides the foundational engine for modern innovation. By mapping the exact physics of the real world into a structured, computable pipeline, it ensures reliability and drives progress across the aerospace, automotive, and consumer technology industries.